difficult than I wanted to. So it's the same subject, but all proofs are different. Muito obrigado. Okay, so we start with the same definitions as last time. So you have valuation. It's a map from a ring brigada to Z, surjective without zero. And it has nu of x, y is equal to nu of x plus nu of y, and also nu of x plus y is bigger or equal than mean of nu of x, nu of y. In particular, the set nu minus 1 of non-negative numbers is a ring. It's called valuation ring for this valuation, and also nu minus 1 of z bigger than 0 is an ideal. Okay, so this ring is called discrete valuation ring. So definition, R is DVR, discrete valuation ring, if R, this should be a field actually. So let's do it for a field. Is nu minus 1 of z non-negative, where nu from the corresponding fraction field to z is a valuation. And we don't take 0. Okay, the example is the periodic valuation which we have considered last time. So example, if R is factorial, the typical example is Z, but you can do it with other rings. You take P is a prime. You take X in R, you decompose it as X is a product over all primes, Pi, Ki, and then P power K, where P and P are coprime, then nu of X is K. This is a valuation. We checked it last time, and it is periodic valuation. And this is the basic example which we work with. Pretty much other valuations don't exist, more or less. Okay. So remark. We had this remark last time. So if you have R is local ring of crude dimension 1, and without zero divisors, then R has only two prime ideals. So it has maximal ideal inside, and this contains 0. It's proper, and these are only two prime ideals. No other prime ideals exist in R. Okay. On the other hand, if you have discrete valuation ring, it's not hard to see that it has no other, it has only this ideal and 0. No other ideals exist. First, this ideal is maximal, because if something doesn't belong to this ideal, it is invertible in that ring. And then if you have and then every ideal in that ring is actually a principal. Well, next slide you will see it. So it has only principal and generated by a power of a certain number, of a certain element. So DVR has only 2 prime ideals. DVR has only 2 prime ideals. And this implies that its Krull dimension is 1. These 2 ideals, this ideal and 0 are prime, and no other ideals exist. Okay. So let's now let me tell you about principal ideals. We had it last time as well. So suppose you have Noetherian local ring without 0 divisors, and so it's called claim 1. So you have R, Noetherian local, and M is maximal ideal. It's unique because it's local. Then R is DVR if and only if M is principal. Okay, so proof, suppose that it is DVR. R is DVR. We take P inside R such that nu of P is 1. It exists because this map is surjective. Then for each x in R, we take P such that nu of x is k. We take P minus k x, and nu of this element is 0, which implies that x is P power k times invertible. And this implies, first, it is this ring is factorial with unique prime, which is P, and all ideals are principal. Of P are principal, of R are principal. So you take an ideal, you take the minimal power of P which sits in that ideal, and it generates it by this argument. So all ideals I are principal. I is P power D, where D is minimum for all x in I, nu of x. Okay, so this implies that every discrete valuation ring is a principal ideal domain. In particular, the maximal ideal is principal. So converse suppose that M, so this is the opposite, the converse. I prove claim 1. Suppose that M inside R is maximal ideal, and then M is principal. You take element X in R, either X belongs to this ideal, P, or X is invertible. This because P is a maximal ideal. And then you have X. We don't actually use the noetherianity. Noetherianity follows a posteriori from being DVR or from being maximal ideal being principal, but you can actually remove it and then it will be a posteriori true anyway. Okay. So X is P power K times invertible. Just use this and apply it inductively. And then this implies that R is factorial. And R is nu minus 1 of Z positive or Z non-negative, where nu is a p-adic valuation for this P. So nu is p-adic. Okay. So being discrete valuation ring is equivalent to having principal ideals or just maximal ideal as principal. Okay, so then this implies the corollary, which I'm going to state now, and it was last time. It was in the previous lectures, it was, I think, proposition 1. Now it's corollary 1 because it's immediately implied by this equivalence. So DVR is local, Noetherian. So Noetherianity follows from this argument. Principal ideals. Ring. And Krull dimension is 1. Okay, this is just what follows from what we already did. So principal ideal is claim 1. Noetherianity is also claim 1. And what else? Yeah. It's local because everything which is not in maximal ideal is invertible. Am I clear? Okay, there was this list. Well, you have already seen it. I'm not going to explain that before it would be one of the last slides. I just wanted to show you that it has lots of different ways of characterizing discrete valuation rings. So it's the same as integral clause, that's the same as maximal ideal is a principal ideal. It's the same as this dimension condition. Yeah. So the most important part of that is that discrete valuation ring is the same as integrally closed under this assumption on dimensions. So if you have local ring which has crude dimension 1, it's DVR if and only if it's integrally closed. Last time it was proposition 2 and it was complicated. So today I will do like high-tech version of the same argument. Well, different argument, but it will be really high-tech because I would use the more conceptual arguments and more important concepts. The notion of projective model is one of the most important notions in commutative algebra. It also belongs to homological algebra, and people use it all the time. So I will spend a lot today about projective models. So now definition. There are two definitions. So the one which I'm going to give now is not a good one because it's hard to generalize for other categories, but it's simple. So suppose you have PR model. Well, it's called P is projective if P is a direct summand of a free R model. What is free R model? It's R model which has a form, just direct sum of several copies of R. So F is direct sum of R with itself lots of times. So for finite, it's sort of clear what it is. For infinite, it's also sort of clear. It's just sum of finite linear combinations of generators with coefficients in R. The important thing is that direct sum is not a product. In fact, product of infinitely many copies of R is not projective, and direct sum is. So direct sum is sort of has basis, and product, well, not that doesn't have any obvious basis. It might happen that it doesn't. So free model is a model which has basis. Okay, so now the characterization of projective models which I am going to give now is in fact the proper definition. The good definition of projective models is this theorem. What is important is that, well, I prove it as a theorem, but you should really remember it as a definition. The proposition. Suppose you have a P is R model. Is projective. If for any morphism phi psi from P to B, and any surjective morphism phi from A to B. So you have this diagram. You have A goes to B. This is surjective. And you have any map from P to B. This is phi, this is psi. And there exists mu making this diagram commutative. So mu is a map from P to A.
So the quadrants go so for every psi and every phi?
Yeah, for every phi and every psi, there exists such a mu. This is equivalent to being projective. Thank you. Okay, so let's prove it. So I have A goes to B. Let's prove it first for free model. So I have free model. So for each generator, E, I, this is generators of this F, it has an image in, so this is psi, you have psi of EI. And let's pick, since A to B is surjective, there exists, let's call it mu of EI inside A, such that phi of mu of EI is equal to psi of EI. So we take pre-image, we take EI, we take its pre-image in A, and we define a map mu on this EI by taking this pre-image. It's well defined because it's to define a map on a free model, it's sufficient to define it on each generator. They're independent. Okay, so I proved you just that this statement is true for free models. So now you have P1 plus P2, P plus P prime is equal to F. So first you extend your map from P to B to F to B just by taking it whatever you like on P prime, for instance, 0. You can always extend your map from P to B to F, to F to B. And then you apply this argument to F. And this makes this diagram commutative on F and then on P as well. Because P is a submodel of F, you extend it to F, so you can, this gives you an extension to P. Was I clear? Let's do converse. So this was the one direction. So we proved that if P is projective, then mu exists. So to see converse, we define now our map. Psi will be equal to phi. So we take F to P surjection, where F is free. So how to find this surjection? You just take any set of generators. I mean, P is, of course, not necessarily finally generated, but it's still generated by some subset. You can take all of elements of P as a generator or just some subset, doesn't matter. The important thing that you would have a surjective map from a free model to P. Okay, so your A is equal to F. So this is phi. This is P. And this is P. Oh, yeah. Yeah, so I told you wrong. I told P is equal to phi, it's wrong. This is, of course, identity. Okay, and we want to find this map mu. So what will be this map? This will be a map such that for each P, its mu of it composed with phi is identity. This is identity. I think on slides I have also hope it's not that wrong on slides. Anyway, so this would be a section. So mu is a section. Is a section. What does it mean, a section? This means that f is mu of p plus kernel of p, or of mu. Sorry? It is injection because the composition is identity, so it can't not. Section? Because this is surjective map, and this is inverse. This is why it is a section. So for each element of F, we decompose it onto, we take its image in P and image and for phi. So F inside F is decomposed to mu of phi of F plus F minus mu of phi of F. This second part belongs to kernel of mu, and the first part belongs to this image. So this is direct sum decomposition, and mu is injective because the composition mu with phi is identity. So this means that F is a direct sum of P and something else, this kernel of mu. And we proved that it is indeed projective. So this, yeah, question?
Could you repeat the argument? So we know that this mu gives an injection. But why do we know that? How do we find the complement?
Oh, this is it. This is a decomposition. So F is mu of P plus kernel of mu. And this is explanation why it is so. You take any F in F, any small f, then F is mu of phi of F plus difference F minus mu of phi of S. Trivially. This belongs to the image of mu, and the second belongs to the kernel of mu. So this implies that you have indeed the direct sum decomposition for F. Okay, so in textbook, you would probably find this definition, at least on homological algebra, because this definition works in any category, like in category of sheaves, which makes no sense, of course. I mean, it's hard to define free whatever, but so this definition is definitely more general, but for models overriding, these definitions are sort of clearly equivalent, so you can use both. Okay. There's another characterization of projective models, which works only for finely generated models, but it is very powerful, and we will use it a lot. So this is an important theorem, which is called dual basis theorem. It's not in the typical commutative algebra textbook for some reason. So I found it in a lecture notes by May, who is a topologist. So probably it's much better known to, I don't know. So it is a characterization of finely generated projective models. You have a certain natural map of tensor products. So theorem. So suppose that M is our model. You have a natural map psi from M to over R, from M to R, tensor over R with M, and this goes to endomorphisms of M. how it takes? Well, you take a, so to define this map, you need to define it on a bilinear map on this space and that space. So psi, you need to define psi in pairs, lambda and m, where lambda belongs to home from M to R, and M belongs to M. And this would be equal to lambda of it will be equal to lambda times M. So lambda, it belongs to endomorphisms of M. Lambda takes an element in M and produces an element in R, and then you multiply it by M, and you obtain an element in M. So this product is an element in the endomorphisms of M over R. So this is an initial map. This is how it is defined. Lots of similar maps, if you look at in textbook, like it's better to say it's to look at in Lang, because he has billions of them for all kinds of maps associating to with tensor product and homomorphisms. This is one of the very typical maps. Okay, so then the following are equivalent. So one, psi is isomorphism. So these two models are isomorphic. Second, identity in M belongs to image of psi. This is an element of endomorphism, it should belong to this image. And the third is M finitely generated and projective. Definitely not injective. Or definitely not surjective. I think it's injective. But it's not surjective even for free model if it's not finitely generated. So about surjectivity, I'm not entirely sure even about surjectivity, but it should be. Yeah, for vector space, it's all trivial. But for rings, there are lots of strange things, so should check. This is a good exercise, so please check it. But it's false for vector spaces if they're not finitely dimensional. So it's true only for finite dimensional vector spaces. And this is actually not hard. You can actually check not entirely, but quite almost. Yeah. The problem is that this is continuous dimensional. This continuous dimensional for countable dimension M. So it's almost dimensional count, but not quite. But you're right. Yeah, it's set theoretic arguments which do it. Okay, so let's do a proof. So you have second. Yeah, first clearly implies second. This is clear. This is isomorphism, then it is an image. And then third implies the first. This is for the following reason. It's sort of clear that this is an isomorphism when M. So this is because psi is an isomorphism when M is R power N. How to check it? Well, you just find a basis in R, And then this gives you a dual basis as home from M to R. And then the elements, if you have EI basis in M, EI dual basis in home from Rn to, well, from M to R. This just takes an element of a basis and takes its coefficient to R and forgets about all other coefficients. Then the basis in so EI tensor, EI star tensor EJ is basis in this tensor product, home MR times M. And then this is actually matrices. These are matrix coefficients. So this is matrix coefficients of A inside a home from M to N. And this gives equivalence between this space and home from M to N. There's a basis there and a basis there. There are both free models with the same basis. This is your basis. So this is actually matrices, if M is free. This matrix is N by N. And this has the same basis, so they're equivalent. And then if you have a direct sum, a decomposition, you just decompose this onto there will be 4 terms in that tensor product, because M is decomposed into a direct sum and M is decomposed into a direct sum, so there will be 4 terms and 4 terms here, and for each of these terms you will have an equivalence. This includes the term where you have M, P here, P here, P here, and P here. So this gives an implication from 3 to 1. Okay, so the only interesting application is from 2 to 3. So step 2. We need implication from the second condition to the third. The rest is elementary. Okay, so let's write this. So we're interested in taking an element in this model which goes to identity. So let's write this element explicitly. You have Fi maps from M to R, and you have Mi belonging to M. And then you would have identity in M. This identity from M to M is equal to sum Fi times Mi. This is how this thing is defined. Okay, now we can apply this map to any M. We would have let's call it F. So I would take F from a free model generated by EI. Oh, freely generated by E1 dot En, where the set of the index, the same, it's indexed by the same set as this finite set of maps Fi and finite set of elements Mi. So this is a free model. It's mapped to M, and F of EI is equal to Mi times F, sorry, it's opposite. F from M to the free model. F of M is equal to sum Fi of M EI. This is a map to a free model. I just use the same F, and here I put EI as generators. Now we have a map. Is it called somehow? The projection. Yeah, it doesn't call. Let's call it pi from this free model to M, taken EI, pi of EI is equal to Mi. Yeah, first, what I forgot to tell you is that, oh, I can tell it now, that if you take pi of F of M, it will be equal M. Because sum of Fi Mi is identity. And this would, if you apply this to M, you'll have precisely identity applied to M. This is because sum of Fi of M times Mi is equal to M by definition. So you have this, and this first, this implies that the model M is finally generated. It's generated by this Mi. And second, you have a projection from this projection pi, and you have a map F, and they're in the, one is there, have F goes to by pi to M, and you have F going in the opposite direction, and you have that pi of F of M is equal M. So this is a section. This is a section of a surjective map from F to M, which implies that F is the direct summand of M, and M is projective. Should I repeat? Okay, so first we notice that, so we have this map, identity of M is equal to sum Fi times Mi. So let's apply it, identity of M applied to M, to an element M inside this model M is equal to sum Fi of M times Mi. And this is equal to M. So this immediately implies that M is a linear combination of Mi. And Mi are generators. They are finitely many. Am I clear? So I just decomposed identity onto a finite linear combination because it's standard product. It's always finite linear combination. So this is our linear combination, which gives you identity, and it also gives a decomposition. I mean, it gives you for free the set of generators for M. Now we take a free model which is generated by a finite set which has the same cardinality as this Fi and Mi. And we obtain a map F which takes, which is written as here. It takes M to Fi M times Ei. So this is this element in R, and this is element in this free model. Right? And then you have a projection from free model to M, taking each Ei to M, to Mi, like that. And their composition is identity. This is what is written there. This is composition of these two maps. Okay? And then this means that you have a surjective map from a free model to M, and you have a section. Precisely like we did in previous couple of slides ago, or previous slide. You have a section of the projection to M, so this means that F is F of M plus kernel of pi. And our M, which is embedded to F by this map, is actually a direct summand. Then it means that it is projective. Should I repeat, or is it clear? Maybe you have questions? So the key argument is that identity has a finite decomposition. And finite precisely because it's tensor product. And tensor product is finite decomposition. So this finite decomposition gives you a finite number of generators, and then it also gives you a section for free. You are quiet. Should I repeat it? Sorry? Yeah, but it is almost trivial. With the decomposition? Yeah, it's worth repeating, thanks. So, suppose you have a quotient of a free model. Every model is a quotient of free model. F goes to M. Of course, if this M is projective, you will have a section. This is like we had last time. Converse is also true. Suppose you have a section. So you have P here, F here. Then consider a decomposition. So I am claiming that a kernel of pi plus image of F is F big. This direct sum decomposition, and then this identifies image of F, which is injective because it's composition with pi. So what we need is pi of F of M is M, which is written there. This is how we define this F and pi. So it is identity. Okay, so we need to prove this. This is proven as follows. You take element x in F, and x is equal to F of pi of x plus x minus F of pi of x. The first belongs to the image of F. And the second, this thing in brackets, it's mapped to 0 under the projection. Because pi of F of x is equal to pi of x. pi of f is identity. And this is, if you project x, it will also give you pi of x, so this difference is 0. And this gives you this decomposition. Image of f plus kernel of pi is equal to all f. It's because every x is decomposed as this on these two components. And this is generally true. If you have any existence of such a section is equivalent to projectivity of M. It's if and only if condition. Okay. Yeah, so should I repeat again? Okay. So let's use this theorem a bit, and we can have a break. Well, we won't use the theorem. Let's have a break now. Nós temos intervalo para 5 minutos agora. Okay. There's a nice set of theorems about how models over local rings finely generated models over local rings work. And it's these theorems start at let model which has that and that property, then it is free. You can do it for flat models. You don't know what is flat, but if you know, you know. Today we'll do it for projective, but it's part of a general setup where you say that every model which is not bad over a local ring is free. Okay, so theorem which I'm going to prove. It's called proposition here. And it's pretty elementary. Suppose you have a finely generated projective model. Projective over a local ring, Noetherian ring. Then P is free. Proof. Well, to prove it, we take a set of generators of the quotient. So we take, let M inside R be maximal ideal. And we take E1 dot En, generators of well, it's elements of P. We generate P over PMP. So this finely dimensional space over a field. K is R by M. So it's finely dimensional vector space. And I assume that they are independent, linearly independent in this space, in the P quotient by MP. This makes sense, right? So you have finite dimensional space. This is finite dimensional because a quotient of a finitely generated model is finitely generated. A finitely generated model over a field is finite dimensional. It's a finite dimensional space. Okay. Now consider a map. So from FRN, this is our free model, to P, which takes a generator and maps it to, so it takes a generator, let's say, call it EI prime to EI. This is generator. This map is surjective by Nakayama lemma. If you remember, Nakayama lemma tells us that if you have any map from M to N models, such that M quotient by Mn to N quotient by Mn is surjective, then psi is surjective. This is a general observation we did a lot, and we used it a lot. It's a really important, it's actually the main consequence of Nakayama lemma. You need finely generatedness for this, of course, but we have it. Okay. So this gives you a surjection. So Rn surjects to P. And since it is a projective, you would have a section. Right? So this surjection has a section, but then the image of this section, so modulo M, this is so this psi and this mu, psi and mu are isomorphisms, right? I mean, they're in the inverse modulo, because Rn quotient by M is P quotient by M, so psi is invertible modulo, is an isomorphic modulo M, so the same is true for mu because it's a section. Then this means that you can apply this version of Nakayama lemma to mu. Then mu is surjective. Okay, this is an isomorphism. We have two surjective maps which are inverse to each other. They are actually both injective and they're, there's no kernel. Okay. Then psi and mu are isomorphisms. So we proved we proved that our model P is isomorphic to a free model. This is done. This is very basic, and this is one of the first things people learn about projective models over local rings, so please don't forget it. Now I'm going to apply all this machinery to fractional ideals. So I'm giving you a reminder about fractional ideals. It has, I'm not going to prove things about them, but we had them a lot. Please ask me questions if something is non-clear. So a fractional ideal is a non-empty, non-zero model. So you have R as contained in K of R. This is a ring without zero divisors. And I inside K of R is fractional ideal if if I is non-zero, and there exists A inside R such that AI sits in R. This definition of fractional ideal. And then you can do lots of nice operations with fractional ideals. So first is this condition is equivalent to, if R is noetherian, this condition is equivalent to finely generatedness, which is sort of clear. If it's I is finely generated, you can take all denominators and multiply by the product of these denominators, you obtain something in R. And conversely, if it's model in submodel in R, it's finely generated by noetherianity. Okay, so nota bene, if R is noetherian, I is fractional, if and only if I is finely generated. The next observation is that you can take products and you can take intersections. They are also fractional ideals. So if I1, I2 fractional, then I1, I2, and I1 intersected with I2 are fractional. And the third observation, so this is sort of clearly fractional ideal, this is slightly less clear. And what is also important that multiplication of fractional ideals is associative, well, it is clear. What is also important is that you can define two nice fractional ideals associated with an fractional ideal. So if you have I, you associated the I minus 1, which is all x inside k of r, such that xi sits inside r. And then you have r of I. It's similar. It's a set of all x inside k of r, such that xi sits inside I. So this is actually a ring. This is not a ring. This is sort of inverse. Next slide, you will see precisely why it is inverse. But what we have now is that these two are also fractional ideals. And moreover, you have this kind of chain of embeddings, which are almost trivial. So I'm not repeating the proofs. So you have R of I contains R, and it contains I minus 1. And also, if I sits in R, then I minus 1 contains R. Two trivial observations. Should I go on? No questions? Now the important notion, which didn't have last time, because I wasn't given a conceptual proof, now I will. Sorry?
Why do we have to define
R of I, you mean?
It's like I is an idea in this K of R?
I of R of I, this one. It's very useful because it will be, if our ring R is integrally closed, then this will be R. This is a characterization, if it's an application of integral closedness, which is used to unravel everything to prove that every local ring, which is integrally closed and Krull dimension 1 is actually a discrete relation ring. This is the key observation. This is why we need this guy. Okay, so definition. I inside K of R is fractional ideal, is called invertible if I minus 1 is R. So we know that there's this, well, I didn't write it, but it's sort of clear that it's contained in R, but it can be smaller. Yeah, it's by definition. So it's by definition, it's contained in R, and it's actually, it's contained in R, and it is contained in I think. Well, we shall see. So now I'm going to characterize fractional ideals which are invertible in a nice way, using the previous arguments about the projective models. It's a very nice theorem. So you have I inside K of R, fractional ideal. I is invertible if and only if I is projective as R model. This is fun because this is intrinsic characterization and this is extrinsic. This depends on the way it sits in KFR and this doesn't. So in particular, we obtain that invertibility is in fact intrinsic notion. It doesn't depend on how you embed your ideal into KFR. It will still be invertible regardless of the embedding. Okay, so let's prove it. So the first part of the proof is very elementary. It's how you obtain invertibility from being projective. So step one. Sorry, now conversely, projectivity from invertibility. I minus 1 contains 1. Then this implies that identity in I belongs to whom from I to R. This thing contains I minus 1 times I. Right? This is there, and you multiply them, and this is equal to I minus 1I. And then I is projective by this. Theorem, which characterizes projective models in terms of having identity sitting there. Sorry? So identity in I sits in that model. This implies projectivity of I. Then I is projective. You want to see the dual projective Bayes theorem? So dual projective Bayes theorem tells us that if identity is there, then I is projective. And now I'm proving that projectivity is equivalent to invertibility. I start with invertible model. I obtain that identity I sits in that tensor product. And this implies projectivity. Any questions? Okay, so this was the easy part. So the other part is also easy, but slightly less easy. So step 2. Suppose we have a linear map, our linear map of fractional ideals. Let's tensor both I1 tensor over R by K of R. Since this sits in K of R, this would give you K of R. Just all elements of I1 are proportional up to elements of K of R, so this gives you K of R. This gives you phi to I2 times K of R over R again, and this is again K of R. And this is a linear map. This map was R linear, so after multiplication it becomes K R linear. And we know that maps from a one-dimensional vector space to one-dimensional vector space are just elements from the field. So phi, this new phi k, for instance, did I have any notation for that? Well, this map, phi k, belongs to k of r. Good. This means that you can consider, we actually had that notation last time, J, I1, I2. This was the set of x in K of R, such that x I1 sits in I2. Then this J is actually a homomorphism. So J, by this step 1, J of I1, I2 is actually homomorphisms over I from I1 to I2. Because we interpret for each phi, we obtain phi k, which is element of K of R, and it has this property. It defines the same map. So restricted, this multiplication by this element in K of R, restricted to I1 gives you I2. Clear? So all homomorphisms from I1 to I2 actually are obtained, their multiplication by some element in this fraction field. Not all of them, but there are some elements which map I1 to I2, and this is precisely the homomorphism over I from I1 to I2. Should I repeat? Is it clear? So you just multiply, how you obtain this? You multiply your I1 by fractions, you multiply I2 by fractions, you obtain, this would be, this, yeah. So I1 sits there. You obtain this funny diagram. I1, it sits in I1 times K of R, which is just K of R. And it goes, you have phi, here you have phi K to I2 times K of R, which is again K of R, and I2 sits there. And this diagram is commutative. So here you have embeddings, like tautological embeddings. Here you have phi, here you have phi chi, and phi chi belongs to K of R. So this phi is an element of K of R, like is written there. Okay. And then this implies, in particular, that I minus 1 is home from I to R. Okay, now we can finish the proof. It becomes one line. Step 3. So if I is projective, you have identity in I belongs to I minus 1, which is home from I to R, times I. This is over R. Because I minus 1 is precisely home from I to R, and this implies that this is actually R, because it contains identity. So 1 belongs to I minus 1 times I, and this implies that you have 1, this is invertible model. So if I is projective, then you have identity, which belongs to the product. So identity belongs to this product. But then you notice that here I had this embedding, I minus 1 to there, but it is in fact an isomorphism now, after step 2. So this is an isomorphism, and we obtained the inverse. The step 1 can be inverted using step 2. Should I go on? Clear? Good. Thanks. Okay, there was a trivial observation. In fact, for some reason, I.T. MacDonald here invokes they invoke the theorem of Lasker-Noether and all the power of primary ideals, making the proof much harder, and you don't need it. So it's very elementary. I remind you that radical of an ideal is a set of all x inside R such that x power k belongs to I for some k. In other words, you take nil radical of quotient R by I, and you take its preimage of this nil radical. This will give you. In particular, when the ring is Noetherian, you can choose this uniformly. For each k, there will be a biggest constant, because you take, so square root of I is union over all k of x inside R such that so that x power k in I, and this union k increases, so it should stabilize. So this k can be chosen uniformly if your ring is Noetherian. Okay, so now claim. You have R is a local ring, no Z divisors, cruel dimension 1. Then, and I is non-zero ideal. I non-zero ideal. Then radical of I is maximal ideal of R. Well, you can do it, start with the radical ideal, it doesn't matter. And here I use the standard exercise in commutative algebra, which we discussed, I think, maybe in this first or maybe on the second lecture, that intersection of all prime ideals is nil radical. Right? This means that intersection of all prime ideals containing I is radical of I. Okay. It's cruel dimension 1 local ring. It has only two ideals. There's something we have discussed. There's 0, a maximal ideal. They're in between. And there is nothing else because all ideals contain 0, all ideals are contained in M, and there is no intermediate prime ideals because of dimension 1. So all these prime ideals are actually maximal ideal. This proves this claim. Okay? So it's very elementary. But it has a funny corollary, which we're going to use. Now, here uncertainty was not used, but now I'm going to use it. So corollary 2. Suppose you have R Noetherian, local, crude dimension 1, M maximal ideal, and T in M non-zero. Non-zero. I forgot this assumption on the slides. It's my error, so it should be non-zero, of course. Then, for some n, you take m power n. This is all products of n tuples of elements in P is contained in T. This is because radical of T is equal to m. And what is radical is precisely the set of all elements in a ring, such that the some power is contained in this ideal. And you can take M uniformly for that argument because of neutrality. Okay. Should I go on? Good. Thanks. Okay, so we have this semi-trivial proposition. So, if you have a ring with projective maximal ideal, then it is local ring with projective maximal ideal, then it is a discrete relation ring. You don't need nothing. Well, you need necessarity, probably. Proposition. So suppose you have R is local, Noetherian, and maximal ideal M is free. Oh, sorry, yeah. Well, M is projective. Then R is DVR, discrete relation ring. Proof. Yeah, non-uncertainty is needed only for implication. From projectivity, we want to obtain freeness. This is something we already had. Every projective model over a local ring is free. So non-uncertainty plus projectivity imply that M is free, R model. This means that M is direct sum of R times EI, where EI are generators. And they don't intersect. But then EI, E2 belongs to intersection. R, E1 intersected with R, E2. R1, the R, E1 intersected with R, E2. Well, this can't happen. It's a free model, right? So this generator, it can't be zero. So it's a non-zero element in this intersection. Okay, then it means that Rm is principal. And we have corollary 1, which tells us that this is discrete relation ring, right? A local ring with principal maximal ideal discrete relation ring. Okay, so this gives us corollary 3. So corollary 3, just write it here. Suppose you have R Noetherian local and maximal ideal invertible as fractional ideal. Then R is DVR. Because then it is projective, then it is free, and you can apply this proposition. Clear? No questions? Okay. Now I can prove this proposition 2, which we already had. So proposition 2 will tell us that if you have a local ring, rule dimension 1, and integrally closed, it is DVR. Last time it was huge, too long, 7 steps. Now it will be only 3, and it's sort of shorter because we used all this machinery with projective models. So proposition 2. The converse immediately follows from, so if you have a DVR, it's integrally closed because it's principal ideal domain, so it is factorial. So suppose that R is rule dimension 1, no other divisors, integrally closed, Noetherian local ring. Then R is DVR. Okay, so step 1. This is precisely the same step 1 which we had last time. You take R of I. It's a subset in K of R, which is finally generated as a ring and as our model. And this is a ring. What is integrally closed? It means that all finite, all elements in K of R which are finite over R belong to R. So this belongs to R. R of I is equal to I. This is the application of being integrally closed, and this is actually equivalent to being integrally closed. This is the only thing we will need for further proofs. So now we can forget that it is integrally closed, and because we already had everything we wanted from integral closedness. Am I clear? Okay. Now we have this step 2. We have M maximal ideal, and we have R contains M minus 1 M, and this contains M. So this is because M minus 1 are elements of K of R which become R after multiplying by this. So this is clear by definition. And on the other hand, if you take an element in M and you multiply it by, well, the other implication is clear because R is contained there. So this is contained in M. Anything which sits in M sits there as well. No, I think I'm doing opposite way. Sorry. Yeah, this. Yeah, but the statement is. I mean, what I said was correct. I just wrote wrongly the embeddings. So the product sits there because of definition of m minus 1, and m sits there because m minus 1 contains R. Okay. So this is intermediate submodel. If m minus 1 m is not contained in M, it has an invertible element because M is maximal ideal. It has invertible element. But then if it has invertible element, you can multiply its submodel over R, so then it is equal to R. M minus 1 M is equal to R. And we're done because in that case, M is invertible, and we have this corollary 3, which tells us that if M is invertible, this is DVR, right? So corollary 3 implies that R is DVR, and we're done. So you can assume by absurd that this is strictly smaller, and this means that you have. So it remains to show that M. Well, we can assume that M minus 1 is not R, so by absurd we can, is not M. So I assume it is M. Okay. So step 3. I use Krull lemma, which tells us that intersection of the powers of an ideal is if you intersect the power of ideal, it will be 0. So this means that you have M is strictly contains M squared, strictly contains M third, and so on. All containers are strict. By Krull lemma, otherwise you would have intersection of all these ideals. Well, they can be 0, but in our case, they are not 0 because our ring is without their divisors. Otherwise, this cannot stabilize. Okay, I take T inside M without M squared. This will be our uniformizing parameter, but so far we don't have it. But what we have from this corollary 2 is that for some n, M power n is contained in the principal ideal generated by T. And I take it in such a way that M power n minus 1 is not contained in T. Well, if T generates M, it cannot happen, but then we're done, because then M is principal. So we can, and we assume that it is not true, so we have this. It makes sense because of that. Okay, and I take X. Is it X? I take X in M n minus 1 without T. So it's a complement. Okay, these two corollaries are not needed anymore. No, this is needed. This one is not. Now I take an element U, Y, which is X by T. And Y doesn't belong to R because X doesn't belong to T. we choose x, which doesn't belong to ideal generated by t, so it's not divisible by t. This is not an R. And then you have xm inside m power n, right? Because x is an m power n minus 1, so this is an m power n, and this sits inside of t. This implies that ym belongs to R. And then y yeah, yeah, and what we have also that by step 1, that R of m is R. Then these two observations imply that y belongs to R, which is impossible. Because we assumed already that I is not in R. This brings a contradiction. So we started with this assumption, and we arrived at absurd. This means that this implies that m minus 1m is equal to R, and we have a diver. Should I repeat? Again, we have this y, x by t. It's not in R by assumption. xm is m power n belongs to t. This means that ym belongs to R. Because because xm belongs to t and y is x over t. So ym belongs to R. Because this ym, I can write it here, for instance. So we have ym is equal xm divided by t, and this is t minus 1 times t. Well, it belongs to t minus 1 times t because xm belongs to t, and this is equal to R. So this means that ym belongs to R. Yeah, this means that y belongs to m minus 1. But m minus 1, by this assumption, m minus 1, m is equal to m. And this means that m minus 1 belongs to R of m, which is equal to R. So this is our assumption, written here. And then this implies that y belongs to R, which is impossible. Should I repeat? Okay, let me finish because we'll have one more slide, and no, we have lots of slides. Yeah, this is something we had. So the easier field, so if your ideal is principal, so p power n in the VR by p power n plus 1 is k, is the R quotient by maximal ideal. Okay, and then this is the last slide I wanted to tell you. I won't have much time to do it, but at least I have some. So there are lots of characterization for discrete valuation rings. So let's write them all down. We have I, R, dvr. And the second, R is integrally closed. The third is maximal ideals principle. The fourth is M quotient by M square is K. Is M by is R by M. It's a residue field. Yeah, and 5 is all ideals are P power N. And finally 6 it's M power N. All ideals are M power N, and the 6 is all ideals are P power N. Okay, so the first equivalent to second by, we just proved it, this previous proposition 2. Third, or proposition 3. Third is equivalent to dvr. This was the beginning, I told you. So now the fourth equivalent to the rest is not obvious. But 5 implies and 6. So 6 is that it is principal ideal domain. So then it is integrally closed, and then it is dvr. So 6 is not hard. And now 5 implies the rest because of 5 should imply 6. Yeah. Well, it's 6 it implies 5, but I will leave it as an exercise. It's obvious. It's just my slides are wrong. Sorry about that. Okay, so the only, this was, I implies the rest. This is clear. Now, and I and 2, I and 3 are equivalent. I and 6 are equivalent, and 6 implies 5. Yeah, and 5 implies 4. So here you have, if you prove that I equivalent to 4, you are done. Now, 4 easily implies 3 because you have a map multiplication by you have P in M without M square, and you have multiplication by P. It takes M power K to M power K plus 1. This is an isomorphism. So in particular, it maps this quotient to that quotient. This is why 1 implies 2, but then converse is also true, and it implies that P generates maximal ideal. Because there are no other ideals all powers of maximal ideal, and if you have an element of maximal ideal which is not an M prime, then this LP gives an isomorphism between R and M. There are no other ideals. Okay. Yeah. So these things are equivalent, and I hope I'm done. Do you have any questions? So we're really out of time, unfortunately. This conceptual proof was more conceptual, but it took more effort to give. Questions? No? Really appreciate questions.